Hello and welcome to the 12th lecture of the Deep Learning course. Today we're going to talk about transformer models. The plan looks as follows. First we'll talk about self-attention, the basic sequence-to-sequence operation that drives all transformer models. Then in the second video we'll look at how to build up this self-attention into a complete transformer model. In the third video we'll look at some famous examples of transformer models and we'll look at the finer details of how they're constructed and how they were trained. And then in the fourth video, we'll look at some of the more advanced tricks that are being studied to improve the performance of transformer models in various ways. So on to the first part, self-attention. In lecture 5, we talked for the first time about sequence-to-sequence layers. And these are neural network layers that take as input a sequence of tensors, usually a sequence of vectors, and produce a sequence of vectors as an output as well, where both of the sequences have the same length, and the direction in which this sequence extends is called the time direction. And the defining property of a sequence-to-sequence layer is that if we change the length of the input sequence, the model can be adapted to handle that without having to change the number of parameters. So the same set of parameters allows us to process long and short sequences. We've seen also how versatile these sequence-to-sequence layers are, how they allow us to do label-to-sequence tasks, sequence-to-label tasks, and even sequence-to-sequence tasks. And in particular, we looked at autoregressive training, an unsupervised sequence-to-sequence task where basically the target is to predict the next character in a sequence. And we also saw that sequence-to-sequence layers can be causal or non-causal, where a causal model is one that can only look backward in the sequence for the current output it's producing, and a non-causal layer is one where we looked at two examples of sequence-to-sequence layers, recurrent neural networks and convolutional neural networks, where the great benefit of a recurrent neural network is that it can, in principle, look indefinitely far back in the sequence, but the drawback is that it requires sequential processing. So we cannot compute one time slice before we've computed the time slice before it. In contrast, CNNs allow us to compute the whole forward pass in parallel for every time slice. But the drawback there is that they have finite memory. They can only look so far in either direction into the sequence. And the aim of self-attention as a sequence-to-sequence layer is to give us the best of both worlds. We want parallel computation and, in principle, the ability to look at any point of the sequence before or after the current output. And to explain self-attention, we'll first look at a stripped-down version called simple self-attention, and then we'll add a few bells and whistles to make it the complete self-attention that is used in practice in all of these transformer models. For now, don't worry too much about where the name comes from. We'll explain all that later. At heart, self-attention is a very simple operation. Here we see a self-attention layer with a sequence of input vectors and a sequence of output vectors. And the basic operation that produces any given output vector is simply a weighted sum over the input vectors. So for every output, we have a set of 6 weights in this case, because we have 6 inputs. We simply perform a weighted sum over the input vectors, and that is our output vector. And we do this for every output, and that gives us our sequence of outputs. Now the trick that makes this special is that this wij is not a parameter of the model, but it's a derived value that we compute from the inputs. And we do that as follows. So here we have the weighted sum that defines our basic self-attention output. And to compute this wij, we first compute a raw weight value w prime ij. So we take the dot product of the ith element of the sequence with the jth element of the sequence, and that becomes our raw weight ij. And once we've computed all these weights, we simply apply a softmax operation to ensure that they are all positive and that they sum to 1. So here's how that looks like graphically. We have a sequence of 6 inputs and 6 corresponding outputs that we want to compute. And for now, we'll look at the computation of y3. So we take the corresponding input x3, and for every vector in the input sequence, we compute a weight by taking the dot product of x3 with that vector. So we'd start by taking the dot product of x3 with x1, which gives us the weight w31. We take the dot product of x3 with the vector x2, which gives us the weight 3, 2, and so on for the whole sequence, including the dot product of x3 with itself. Now that we have these 6 weights, we take the softmax. So after this, all the weights are positive and they sum to 1. Then we multiply each input vector by the weight that we've just computed, and we sum them all up, and that gives us the vector y3. And we do the same thing for all 6 output vectors. Now, of course, if we do this naively, it would involve a lot of loops, and we don't like loops in deep learning. We want to vectorize our operations. Luckily, this operation is a very easy one to vectorize. We do that as follows. To compute all the raw weights of all inputs and all output positions I and j, we can simply compute a large matrix of all dot products of x with itself. So this matrix W prime contains every dot product of every input vector with every other input vector. To apply this softmax operation, we simply apply it to the matrix row-wise, so that the elements of all rows are positive and sum to 1. And then we simply multiply this weight matrix with our input matrix X to give us the matrix Y, which contains all the weighted sums computed in one matrix multiplication. Now, to properly understand what's happening here, I'd like to point out a few things that you may not immediately have noticed. The first is that in this particular version of self-attention, simple self-attention, the weight from an input vector at one position to the same position, so the weight II, where from xi to yi, is usually the biggest, because this weight is defined by the dot product of a vector with itself, and that's usually a higher value than the dot product of a vector with some other vectors. This is not a big problem. It just means that what this simple self-attention is doing is essentially keeping every input vector the same, but mixing in a little bit of the values of the other input vectors according to this weight. And we'll add a few simple mechanisms later that will allow us to change this behavior if necessary. Note also that simple self-attention like this has no parameters. There's nothing we can do, no numbers we can set to change the behavior of the sequence-to-sequence layer. Its behavior is entirely driven by whatever mechanism generates these input vectors. So for instance, if we take one embedding layer and stick one simple self-attention layer on top of it, then the embedding layer entirely drives the behavior of the model. Thirdly, and this is probably one of the bigger reasons why self-attention works so well, note that it is fundamentally a linear operation. The whole of self-attention is one matrix multiplication of W by X resulting in Y. And of course, W is derived from the values of X. But if we ignore that for a second and we look at the computation graph, then we see that at the bottom here, where we express just this matrix multiplication, then we see that at the bottom here, where we express just this matrix multiplication in the purple part of the computation graph, that's purely linear. So along those lines, the gradients will be those of a linear operation, i.e. non-vanishing gradients. Over the teal line, there's a softmax. So there we get a non-linearity at the price of potentially vanishing gradients. So in this way, we get the best of both worlds separated into two paths of the computation graph. A linear operation with non-vanishing gradients and a non-linear operation with vanishing gradients. Another bonus, note that self-attention has no problem looking far back into the sequence. In fact, if we contrast it with the recurrent neural network, then we see that in the recurrent neural network, the further back we go into the sequence, the more computation steps there are between an input vector and an output vector. That's not the case for self-attention. At every point in the sequence, there are as many steps between that input point and any of the output points as at any other point in the sequence. This is because at heart, self-attention is really more of a set model than a sequence model. As we've set it up, this simple self-attention, the model has no access to the sequential structure of the input. And we'll fix this later by encoding the sequential structure into the embeddings, but that's something for the next video. For now, we'll just look at this self-attention operation as a set, as more of a set-to-set layer than a sequence-to-sequence layer. And another way of saying this is that self-attention is permutation equivariant. That is, if we permute or shuffle the input sequence, then it makes no difference whether we first permute and then apply the self-attention, or first apply the self-attention and then permute, we get the same result. So that's the basic operation of self-attention. Now, before we move on, it pays to build a little bit of intuition for why this works so well. And one of the big reasons why it works is the power of the dot product. So here's an illustrative example of how we can think of these dot products and what they express. And we'll move out of the domain of sequence-to-sequence learning for a bit and into the domain of movie recommendation. Imagine that we have a set of users and a set of movies, and we have a set of likes of which users like which movies, an incomplete set of likes. And our job is to predict which other movies these users might like. Now, one thing we might do is to collect feature vectors for each of these users and for each of these movies. It might look something like this. We could collect for all the users the extent to which they like different genres like comedy, action, and romance, and then for each movie, the extent to which the movie has romance, action, or comedy. And if we collect the feature vectors like this, then we can simply take the dot product to get a good prediction for how much the user will like the movie. Because if we take the dot product, we get these terms that are just the feature of each user multiplied by the corresponding feature in the movie. And the first thing to notice here is that the dot product very intuitively takes into account the signs of the features. So if a user likes romance and a movie has romance, then these two values will multiply and increase the score. But if a user doesn't like romance, and their feature vector actually has a negative value at that position, and a movie doesn't contain romance, or is unromantic to the extent that it also has a negative value at that position of the feature vector, then the two minuses will cancel out, and the score will also increase. And if the signs don't match, if a user doesn't like romance, but a movie contains lots of romance, then that term of the dot product will become negative, and it will actually decrease the score. Secondly, the magnitudes of the values in the feature vectors behave very naturally. If a user is fairly ambivalent to romance, then that part of the feature vector will be close to 0, and whether or not the movie has a lot of romance or not, that term will not contribute much to the total score. And if we don't have feature vectors like this, or we don't feel like collecting them, then we can just learn embedding vectors instead of feature vectors. And that's the basic mechanism behind a lot of recommender systems. So how does this mechanism work in a self-attention model? Well, to illustrate, let's set up a very simple classification model with a simple self-attention layer. Here we have a model that contains two layers, one embedding layer that transforms the input words to input vectors, one simple self-attention which leads to an output sequence, and the vectors in the output sequence are summed together to give us a single vector from which we perform the classification. And in this case, our classification task is to take in restaurant reviews and to perform sentiment classification, to predict whether or not the review is positive or negative. Now, if we did this without the self-attention layer, we would essentially have a model where each word can only contribute to the output score independently of every other word. This is known as a bag of words model. And in this case, the word terrible would probably cause us to predict that this review is negative. In order to see that it might actually be a positive review, we need to recognize that the meaning of the word terrible is moderated and in fact inverted by the presence of the word not. And this is what self-attention can do for us. So in this case, what we would hope that the model would learn is that the words not and terrible can interact in an important way for this task. So we would hope to learn that the embedding vector for the word not is learned in such a way that it has a low dot product with the embedding vector for the word terrible, so that if the two occur together in a sentence, we can lower the probability of terrible having a meaning that contributes negatively to the score, because there is a possibility that the word not occurs in a way that inverts the meaning of the word terrible. We can't be sure, of course, with one self-attention layer, but with the features we will add later and with a larger stack of self-attention layers, that problem can be solved as well. let's move to the extra features that we can add to self-attention to make it a little bit more flexible and a little bit more powerful. And we'll look at three different features. The first is a scaled dot product. The second is a few transformations added called key, value, and query transformations. And the third is multi-head attention, which essentially boils down to applying multiple self-attentions in parallel. But first, scaled self-attention. The problem we're trying to solve here is that as the dimensionality of the input vectors grows, so does the average size of the dot product. And that growth is by a factor of the square root of k. So if we divide by the square root of k, then we normalize the average dot product, which keeps the weights within a certain range where we don't suffer from vanishing gradients on this softmax operation. So this is a very simple trick that can really help learning. For the second feature, we need to recognize that every vector in a self-attention operation occurs in three different positions. First, as a vector that is used in the weighted sum that ultimately provides the output, indicated here in purple, and we call that the value. Second, as the input vector that corresponds to the current output, matched against every other input vector. This is called the query. And third, the vector that the query is matched against, which is called the key. And these names derive from a way of thinking about this mechanism as a kind of soft version of a dictionary that you see in any programming language. For instance, in PyTorch, you might define a dictionary of three elements like this, where we have some keys mapped to some values. So creating this dictionary in Python would in memory create this table. And then if we want to retrieve something from the dictionary, we ask it for the value corresponding to a particular key. And the thing we ask it is called the query. And the pairs in the dictionary, of course, are called the keys and the values. And we can think of our mechanism, our attention mechanism, as a kind of softened version of this, where the key, the query, and the value are all vectors of the same size. And instead of having a query that matches only one key, every key matches the query to some extent, as determined by their dot product. And instead of returning a single value, that of the key that matches the query, we return a mixture of all values with softmax normalized dot products as the mixture weights. And in this way of looking at our mechanism, self-attention is just an attention mechanism with keys, queries, and values all coming from the same set. And that's where the name self-attention comes from. So to make self-attention a little bit more powerful, we can introduce some transformations for these three different roles. So that even though we're using the same vector in all three roles, they can behave differently depending on what role they're taking on. And we do this simply by linear transformations. So for every role, we introduce a weight matrix and an associated bias, and we compute a key vector by passing the input vector through the key transformation, the query vector by passing the input vector through the query transformation, and the same for the value. So this makes the self-attention operation a little bit more flexible in what it can do. And note also that because we've now introduced these transformations, the self-attention operation has some parameters. So the operation itself now also has some numbers that we can change to influence the behavior of the layer. The final feature we will add is what's called multi-head attention. And the necessity for multi-head attention derives from the idea that different words relate to each other by different relations. So for instance, the word terrible in this sentence relates to the words not and to, in that the words not and to moderate and invert the meaning of the word terrible. So the presence of the words not and the presence of the word to change the meaning of the word terrible, but the relation between the word restaurant and terrible is completely different. The word terrible describes a property of the restaurant. Now, in order to allow the network to model all these different kinds of relation in one self-attention operation, we split the self-attention into different heads, which are basically self-attention layers applied in parallel. And in practice, that looks like this. We start with an input sequence. We pass the input sequence through some linear operations to decrease its dimensionality. So here we have a two-headed self-attention. So we pass the input to two projections down to a lower dimensionality, W1 and W2. Each is fed to a separate self-attention, so we have self-attention 1 and self-attention 2, each with their own key query and value transforms. We get 2 sequence vectors out, which we concatenate and pass through a final output transformation to give us the output sequence. Now note that there are 2 different ways of implementing this. As we've drawn it in the previous slide, we first multiply each input vector x by this gray matrix here, which turns it into a vector that will be split into 2, one input for each head, and then the input for each head will be multiplied by another matrix to produce its key, by another matrix to produce its query, and by another matrix to produce its value. But since these 2 operations are applied in sequence, and they're both linear operations, we can also multiply them together to produce one equivalent linear operation. And if we do that for each one of these 3 matrices on the right, once for the key, once for the query, and once for the value, what we get is 3 different matrices that immediately produce the key, the query, and the value to go to the different heads. And what this shows us is that the multi-headed self-attention, if we apply it in this way and we ignore the WO transformation that is applied after concatenation, the number of parameters for the single head self-attention and for the multi-head self-attention are the same. So in this sense, we are not adding a lot more parameters by splitting the self-attention up into separate heads. And that's the last feature we wanted to add. So our self-attention is now complete. So to recap, we've introduced self-attention, which is a sequence-to-sequence layer that allows for parallel computation and unbounded long-term memory. It's fundamentally a set-to-set layer. It has no access to the sequential structure of the input. This is something that we need to solve later on. And a large part of the behavior comes from the parameters upstream. Now, the real power of the self-attention comes primarily from its simplicity and its cheapness to compute. This means that we can stack a lot of self-attention operations together and build very large and deep models with them. And these are called transformer models, and that's what we're going to be discussing in the next video.